Hi, my name is Lasse Peters, and I would like to present to you our work on learning mixed strategies in trajectory games. Dynamic game theory, which is the focus of this work, studies the strategic interaction of multiple players with individual objectives over time. As a running example throughout this work, we considered the game of tag, for which you can see a real-world example here. This kind of problem is particularly interesting since competitive play in this scenario requires players to maintain a level of unpredictability. To highlight this challenge, we consider a simplified model of the tag game played between a point mass pursuer and evader with positions constrained to a polygonal region. This problem can be cast as a coupled optimization problem in which the objective of the first player, the pursuer, is to minimize the distance to their opponent while the evader seeks to do the opposite. A key challenge with this formulation, however, is that it only considers deterministic behavior, which may be exploited by a competitive opponent. For example, consider the scenario shown on the right. If here the red pursuer can predict that a rational evader would go to the top, they could chase them down into that corner. And to address that challenge, the goal of this work is to compute strategically randomized, so-called mixed strategy solutions to trajectory games. To this end, we propose a lifted formulation of trajectory games in which players now optimize their expected cost by choosing both the weights and the support of a categorical distribution over multiple trajectory candidates. And at runtime, players sample from this optimized distribution to minimize their expected cost. You can see an example of such a lifted strategy on the right, where now the evader randomizes between either going left or going right, and thereby also forces the pursuer to consider multiple options. While this formulation does indeed admit non-exploitable solutions, it unfortunately also introduces a computational challenge since it drastically increases the problem size. And therefore, the second contribution is that we propose a novel computational method to solve these lift games efficiently. The key idea behind our approach is that for given trajectory candidates of our players, we can rapidly compute the equilibrium mixing weights Q by first evaluating each player's cost for all possible trajectory combinations and then solving a bimatrix game over the resulting cost matrices A and B. For the resulting equilibrium mixing weights and cost matrices, we can then directly compute the expected cost for each player. And the key insight underpinning our method is that this entire computation is differentiable. In particular, we show that a bimatrix game can be differentiated efficiently. We use this gradient information to train a trajectory generator for each player, which predicts competitive trajectory candidates for given game configurations. And by embedding a differentiable trajectory optimization layer in each of these generators, we further ensure that the generated candidate plans remain feasible throughout the learning procedure. The resulting structured learning policy admits inference and gradient computation within milliseconds on a standard laptop. To demonstrate the effectiveness of this approach, here we show our method learning from scratch in receding horizon self-play for the tag game. Within only 2 minutes of training, we are able to learn highly competitive mixed strategies for this problem, for both players. So we perform a range of evaluations of this method, for which I would like to highlight the following main results. First, when comparing against the baseline, which uses sampling to discretize the game, we find that such an approach requires many samples to match the performance of our learning-based method. Further, in decentralized head-to-head competition, we find that lifting provides a competitive advantage over non-lifted formulations of the tag game. And finally, we also obtained preliminary results which demonstrate that our method scales even to many player general sum settings, like the 10-player collision avoidance scenario shown on the right. So to summarize, the main takeaway of our work is that we enable the efficient computation of mixed strategies for competitive play by combining differentiable games with trajectory optimization in a structured learning framework. For more details, please come see us at the poster. We have poster 20, or visit the project website below. Thank you.